So we have data. Data consists of data points. Let's make them blue. So, okay, this is data. Second component was a model. What is a model? What is a model within this course? A set of maps. So one model could be, what model do you know about? What is the most simple model you can think of, or a simple model you can think of? Linear, yes. So the set of all linear maps. So here's one linear map. Here's another linear map. So this is a linear map. It reads in the feature. And outputs a prediction for the label. So I forgot to label the axis. So this is the label. And this is the feature. Feature X. Okay. So now we have data, we have a model, a set of different hypothesis maps. What else do we need? How do we choose the best hypothesis? How do we decide or choose between different hypotheses? We need a loss function, exactly. So we need to measure somehow the difference between the prediction. So here, this is would be the predicted label value for this data point. And here's the true label value. So this would be the true label value. Let's say this is the second data point, data point 2. Then the numbering is arbitrary, but we just need some numbering to be able to speak about data points. So we need to index them. This is the label of the second data point. This is the feature value of the second data point. And here we have the predicted label of the second data point, because the predicted label of the second data point, by the way, is given by the value of the hypothesis evaluated at the feature of the second data point. Yeah, and what we do now, we need to somehow measure this loss. So what loss functions do you know? Squared error loss. So we could take y hat, the predicted label for the second data point, minus the true label of the second data point, and compute the square of it. Or yes, another option would be we use the absolute value. We use the absolute value. Okay, but this is just the loss for one data point. We can compute also the loss for this data point here. How do we combine these individual loss values that we get for each data point? We compute the average, yes. So what we do in machine learning, we compute the average loss. We sum over all data points. These are numbered by I. And let's stick to the squared error loss. We compute the difference between the predicted label for the ith data point minus the true label for the ith data point and square it. And then we might normalize it. But this normalization factor is not so important. It's mainly for convenience. And then, so how does this depend on the hypothesis? Well, this predicted label here is given by the hypothesis evaluated at the feature of the ith data point. So this depends on the hypothesis via this predicted label minus y squared. Okay, so what we do now in machine learning is a machine learning method does nothing but finding or tuning or learning the hypothesis out in the set of all possible hypotheses that makes this error as small as possible. This is called empirical risk minimization. We could also call it, this is the training process. So we want to minimize this quantity here, this objective here, as we vary this hypothesis. Okay. And how do we do this in Python? How do we minimize this empirical risk? How do we solve this? What function do you normally use? Which method do you use to solve this optimization problem? Yes, dot fit. So if you say the hypothesis space is the optimize here my. So if you say that the hypothesis space, so this function must be of the form a linear function. So some weight here or parameter that multiplies the feature plus some other feature that we add, which is sometimes called bias or whatever you want to call it, or offset. So instead of tuning this hypothesis, we can tune the weights. And how do we do it? Well, we have a function which is called linear regression dot fit. And how do we tell this dot fit function the data points? So remember this dot fit function here solves this optimization problem. And in this optimization problem, we must somehow input the data points. So how do we input the data points into this dot fit function? With an NumPy array. So you typically, in your assignments, you constructed an NumPy array X and an NumPy array Y that you used as parameters of this function. Let me check if this is actually true. So let's look here. So what I tell you now is basically implemented in these methods that we allow you to use. So if you look at the machine learning methods, and you look up linear regression, there is a function called dot fit. Here it is, dot fit. And what this dot fit function does, it solves this optimization problem. And as input, you input the feature values of all data points in this NumPy array X, and you input the labels of all the data points in the NumPy array Y. And if we now go back to my drawing, so we get then an optimal weight vector. So we hit the dot fit function and we solve this optimization problem and get the optimal parameters. W1, let's call it star because it's optimal, W0 star. So do you know where in Python is this? Are these optimal weights stored in this linear regression class? How can you read out these optimal weights that minimize the average squared loss? Well, there is an attribute. Yes, I see it already. There's an attribute called coef. How is it called in Python? Attribute. Yeah, it's called attribute. Coef. And this coef underscore here, these are the weights, the optimal weights for the linear map. That is determined, that is computed by the dot fit function. It is then available in the coef attributes. However, do you actually need this optimal weight vectors? You actually, what you're really interested in is not the optimal weights themselves, but you're interested in the optimal predictor. So you want to know, you want then to use the optimal linear map, which is defined by this optimal weights. So it's W1 star times X plus W0 star, W2. But often you're not interested in the internals of the function. So you're not interested in this optimal coefficients. You're just interested in applying the optimal predictor. And do you know how you can apply this optimal linear predictor without using the coef attribute? There's another function. Yes, that's the predict function. The predict function, linear regression predict, oh my God, predict. And this needs as input only the features, okay? Because here you only apply the optimal, the learned or trained linear hypothesis to any data point for which you only know the features. That's the difference to the .fit function. In the fit function, you also need the labels because you need to compute, you need to be able to compute the squared error here for training, for finding the optimal parameters or weights of the linear map. Okay. But in practice, you might not be interested in the weights. Does any one of you have an idea why it might be interesting to look at the weights and not just then blindly use the predict function? What could be, in particular, when you have, let's say you have not only you don't have a single feature, but you have a feature vector. Let's say you have n features of a data point, and you have learned an optimal linear predictor using linear regression.fit. It works exactly the same for more than one feature, and you apply it to a data point with a feature vector x. And so you then have the first weight, optimal weight times the first feature plus blah 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 plus the optimal weight for the last feature. So you could do this, compute this using the predict function, but why might it be useful to look at these weight values or parameter values that are stored in the coef? Very good, to see which features are relevant. So nowadays, people like to get explanations or some form of insight into predictions. And if you use a linear predictor, then you could say, well, I got this prediction because the weight for the first feature is by far the largest. So the first feature drives the prediction, is most important. And the first feature was like this or that. So the first feature was positive and the weight 1 is non-negative and large. So the output, the predicted value must also be positive, something like this. So you could use, or you might be interested in the actual values of the parameters, or in this case of the weights, the coefficients of the linear map, to get an interpretation of the machine learning method. But you might also just be interested in making prediction. And then you don't need to know what the weights are. You just want to apply, a good predictor, a learned predictor, using the predict function. Okay, so yeah. By the way, so we have here a linear model, and now again, I prepared several quizzes today. I would like to know from you, which methods do you know which use the linear model, which use the set of linear functions? Which machine learning methods? I have offered some options. You can choose more than one option. Which one of these machine learning methods, so the first one is decision trees, the second one is artificial neural networks, the third one is linear regression, logistic regression, and support vector machines. Which one of these methods, might be more than one, use a linear model under the hood? Yeah, now it's a bit slower, the response. It's a bit more challenging. Come on, we only have 75%. almost 90% response. Yeah, don't be shy, these are anonymous surveys. I have no means to assign a response to a name, a student name. Yes, almost there, 92% response rate. Maybe some students drop as we go. So, okay, let's end it here. And I want to share the results. So 20% consider decision trees to use a linear model, artificial neural networks, 28%, linear regression, 100%, very good, very good. Logistic regression, support vector machine, a bit more. Yeah, it goes into the right direction. The results go into the right direction, I would say. Yeah, decision trees, they are typically nonlinear. I mean, one can think of a trivial decision tree, which always outputs a linear combination, then it's a linear function, yes. But typically with decision trees, so maybe let me illustrate this here in this picture. So with a decision tree, when you, let's say we have a single feature and a single label of data points. I'm looking so much forward to using a blackboard again, I must say. So a decision tree can do something like this easily. This is nonlinear in the feature, in the original feature. An artificial neural network can also do something like this in a single feature. So artificial neural networks and decision trees typically use larger spaces than only linear functions. But linear regression, yeah, linear regression, of course, this is not a big surprise, uses linear maps, but also logistic regression. Also logistic regression uses linear maps and also support vector machines. As they come off the shelf, they use linear maps. So they all use functions of the form h of x is some weight times x. Okay. So what is then the difference? Can anybody of you tell me then the difference between linear regression and logistic regression? The label values and the loss function. Yes, very good point. So the model is the same. Logistic regression and linear regression use the same model, but they differ in the other two components. So in the data. So for logistic regression, we use data with binary labels. So we could define the label values be 1 or 0, two label values. And have these data points here. And logistic regression uses a linear map as a model, but it evaluates the quality of a particular linear map, or let's more precisely, the quality, the usefulness of a particular choice for this weight using the logistic loss instead of the squared error loss. Okay, and also the support vector machine uses a linear map as a hypothesis. or a linear model as hypothesis space. But it uses a different loss function, which is called the hinge loss. So SVM uses a thing called the hinge loss. Logistic regression uses a loss called logistic loss. And linear regression uses which loss? Squared error loss. Or if you average it, you call it the mean squared loss, or MSE, squared error loss. Okay. So yeah, but all these three methods, these are three different machine learning methods, but they all use linear models. These are all examples of linear methods, but they use different loss functions. Could we somehow group them? Which one of those are classification methods? SVM and logistic regression, these are classification methods, because the label values here for SVM and logistic regression, you use labels which belong to label values which belong to a binary set, for example, 0 or 1. Or another example could be -1 and 1. It's arbitrary. You can use any set with two different elements. Yeah, by the way, the formulas for the logistic loss, for example, they look different if you use different encodings of the label values, but the basic, the mathematical structure is the same. It's just the appearance of the logistic loss might be different if you use different appearances for the label values. If you use 0, 1, the logistic loss looks different than when you use label values -1 and 1. But the object itself, the loss function is the same. It's just the formulas, the appearance of this loss function is different depending on the label values that you use. Okay, yeah, so much for training. I would suggest we have now a 5-minute break and continue at 5:10 with validation and model selection.